Hello, I am Kunal. Welcome to our Statistics Fundamentals series. I am excited to cover one of the most essential topics in data analysis, that is, descriptive statistics and data summarization. Over my 20 years working with data from small startups to Fortune 500 companies, I have seen countless analysts jump straight into complex models without truly understanding their data. That's where this foundation becomes critical. In this presentation, we'll explore the numerical tools that reveal what your data is really telling you. By the end, you will have a solid grasp of how to summarize, understand, and communicate your data effectively. So let's dive in. Let me start with a personal story. Early in my career, I was analyzing customer churn data for a telecom company. The mean customer lifetime value looked perfectly acceptable. But when I dug deeper into the descriptive statistics, I discovered something fascinating. There were two completely different customer segments hidden in that data. This is the power of descriptive statistics. They are not flashy, they won't make any headlines, but they are absolutely foundational. Here are the key reasons why they matter. First, they reveal patterns hidden in your raw data. Numbers in a spreadsheet are meaningless until you calculate mean, median, and standard deviation that bring out the story. Second, they help identify outliers and anomalies. Those outliers might be data entry errors, or they might be your most valuable customers that you need to know. Third, they enable data quality assessment. Before you build any model, you need to understand if your data is clean, complete, and reliable. Descriptive statistics are your first checkpoints. Fourth, these measures form the foundation for statistical inference. Every hypothesis test, every confidence interval, every model we build later will rely on these fundamental concepts. And finally, and most importantly, they enable informed decision making. In boardrooms and stakeholder meetings, people don't want to hear about p-values or model coefficients. They want to understand what the data shows. Descriptive statistics are how you communicate that very clearly. Descriptive statistics break down into two complementary categories, and I want to see them as two sides of the same coin. On the left, we have measures of central tendency. These tell us where the center of our data lives. We have three measures over here: the mean, the median, and the mode. The mean, which is the average, which is nothing but the sum of all values divided by the number of values that you have. The median, which is literally the middle value in your data when you sort your data. And the mode, which is the value that appears most frequently in your data. These three measures answer the fundamental question: what is a typical value in my dataset? On the right, we have measures of dispersion or variability. These tell us how spread out our data is. Think of central tendency as answering where and dispersion as answering how far. We have range, variance, and standard deviation. Quartiles and interquartile range as some of the measures for dispersion or variability. Range is nothing but the difference between the highest value and the lowest value. Variance and standard deviation actually measure average distance from the mean. Quartiles and interquartile range, or IQR, which shows us where the middle 50% of our data falls. Together, these two categories give you a complete picture. A mean alone is meaningless without understanding the spread. It's like knowing the average temperature in a city. You need to know, and if it swings between 50 or 90 degrees, or if it stays stable at 70 degrees throughout the year. Let's dive deeper into the first measure of central tendency, that is mean. The formula is quite simple. In plain English, you add up all your values and you divide that with the total number of values you have. Here's a simple example. If your data set has these 5 values, 2, 4, 6, 8, and 10, you add them up and you get 30. And then you divide these values by 5 because you have total 5 values. You get a mean of 6. Now, here is what I want you to remember about the mean. First, it's the most intuitive measure of the central tendency. When someone asks what's the average, the mean is what they are thinking of. Second, it uses all the data points. Every single value in your data contributes to this calculation. This is mathematically elegant and statistically very powerful. Third, and this is critical, that it's sensitive to extreme values. If you have one outlier, then the main will get pulled towards it. I've seen this full analysts countless number of times. If you're analyzing household income and you have Bill Gates in your data set, the mean becomes meaningless. Fourth, it works best for symmetric distributions. If your data is roughly evenly distributed on both the sides of the center, the mean is perfect. But with skewed data, you need the median as a reality check. In practice, always calculate the mean, but please don't stop over there. Always look at the median too. Now let's talk about the median, the value that literally sits in the middle of your data when you sort it from lowest to highest or highest to lowest. For the data set that we had, 2, 4, 6, 8, and 10, the median is 6 because it is sitting in the middle at the third place. For the even number of values, like let's say if you have 1, 3, 5, and 7, the median is the average of the two middle values. In this case, 3 plus 5, and we take an average because we're having two values, so it comes out to be 4. Here is why the median is so valuable. First, it's robust against extreme values. If you add a billionaire to the group of middle class earners, the median will barely move. The mean gets dragged along dramatically. In my experience, this robustness makes median more practical than the mean in the real world. Second, it's better for skewed distributions. When your data has a long tail in one direction, which is incredibly common in real life cases, the median tells you what a typical value really is. Third, it's incredibly easy to interpret. Anyone can understand that 50% of the data falls below the median, 50% of the data will fall above the median, and that's very powerful communication at the end of the day. Fourth, it's practically essential for certain analysis. In salary surveys, real estate valuations, income studies, anywhere you know the distribution is skewed, the median is not just preferred, but it's the standard. Here is my rule of thumb. If your mean and median are very different, that tells you something important about your data's shape. The gap is a red flag worth investigating. Now moving on, the mode is the simplest measure to understand. It's just a value that appears most often in your dataset. Let's look at this example where we have these values 1, 2, 2, 2, 3, 4, and 5, 5. The 2 value appears 3 times more than any other value, so the mode of this data is 2. Now here is what you need to know about the mode. Firstly, it's the only measure usable with the categorical data. If I ask you to calculate the mean of red, blue, green, red, blue, red, red. What's the possible? What does that even mean, right? But the mode, simple, red. It appears most often, so red is the mode. Second, you can have multiple modes, bimodal or multimodal distributions. If two values appear with the same highest frequency in your data is definitely bimodal. This actually tells you something important, that you might have two distinct groups in your data. Third, the mode is less commonly used than mean or median in quantitative analysis. It is less mathematically flexible and hard to work with in the formulas. Fourth, it's incredibly useful for identifying popular categories. Which products do customer buy most? What are the most common age groups in your customer base? These are board questions and they are important for business intelligence. In my experience, mode is your friend when you are working with categorical data or when you want to identify what is most popular or what's most common. But for continuous numerical data, you will almost always rely more on the mean or the median. Now we shift from the measures of center to the measures of spread. These tell us how much variability exists in our data. Let's start with the range, which is the simplest, right? Maximum minus minimum. It is quick, it's intuitive, and everybody understands it. But here is the problem. It's incredibly sensitive to outliers. If you have one extreme data point, the range will explode. I worked on a data set once where one data entry, a misplaced decimal point, caused the range to be 10 times larger than what it should be. The range is your quick screening tool, but not your robust measure. The interquartile range or IQR is far more sophisticated. Here is the concept. Divide your already sorted data into 4 equal parts. We call them quartiles. Q1 is the 25th percentile. Q2 is the median. Q3 is your 75th percentile. And interquartile range is nothing but Q3 minus Q1, literally the range of the middle 50% of your data. Why is this better, right? Because it completely ignores the extreme values. The top 25% and bottom 25% are excluded from the calculations. This makes interquartile range or IQR more robust. It's not fooled by the outliers. In practice, I use IQR constantly. It's one of the best ways to identify outliers. Any point beyond first quartile minus 1.5 times interquartile range or third quartile plus 1.5 times interquartile range is considered an outlier by the standard definition. Think of range as your first impression, IQR as your deeper understanding of your data. Now we arrive at what I consider the most important measure of variability in statistics, the standard deviation. Don't look at the formula, it will look very complex, but the concept is very elegant. It's the average distance of each data point from the mean. Let me break down the logic. First, you calculate the deviation of each point from the mean. Then you square those deviations. Then you average them. Then you take the square root to bring it back to the original units. Why this specific procedure? Actually, the math works out very beautifully. Standard deviation is stable, consistent, and widely applicable. Here is why standard deviation is considered the gold standard. First, it's the most important measure of variability in machine learning and statistics. When we build models, we constantly reference standard deviation. When we scale features, we divide by standard deviation. It's fundamental. Second, it's used in feature scaling and normalization. One of the most common feature scaling technique is z-score normalization, which divides nothing but by standard deviation. Third, it's essential for anomaly detection. Beyond two-third or second or third standard deviation, the values that you will observe, right, from the mean are statistically outliers which are worth investigating. Fourth, it works beautifully with normal distribution. Approximately 60% of data for a normal distribution falls within one standard deviation of the mean, 95% within two standard deviation, and 99.7% within the three standard deviations. If I had to pick one measure to describe dataset's variability, it would always be standard deviation. It's like statistical hammer for which many nails exist. Variance is the conceptual sister of standard deviation. It's simply standard deviation squared. You might wonder, if standard deviation already exists, why do we even need variance? Here is the reason why we need variance. First, variance is easier to work with mathematically. If you are deriving formulas, when you are doing theoretical calculation, variance eliminates the square root. This makes math much cleaner. Second, variance is a key component in many statistical techniques, be it regression analysis, ANOVA, factor analysis, they all work with variance under the hood. Third, large variance values indicate greater variability. Interpretation is the same direction as standard deviation, just a larger number. Fourth, in theoretical statistics, variance is often the preferred form. When proving theorems or doing statistical inference, mathematicians prefer to work with variance because equations become very much simpler. Now, here is a practical insight. In applied data science, we usually report standard deviation because it is in the same units as the original data. Variance is typically in the squared units, which becomes harder to interpret. But in models and theoretical work, variance is doing the heavy lifting behind the scenes. They are two sides of the same coin: variance for theory and computation, standard deviation for interpretation and communication. So far, we have discussed where data is centered and how spread out it is. But data also has a shape, and that shape also matters. Skewness measures asymmetry. Imagine your data distribution as a shape. Is it perfectly symmetric, or does it have a tail on one side? Positive skew, also called as right skewed, means that the tail points to the right. The mean gets pulled towards that long tail. Income data is typically right skewed. There is a long tail of high earners. A skewness value of plus 0.45 indicates moderate right skew. On the other side, negative skew or left skewed means tail points towards the left. Test scores sometimes show left skew when most of the students do fairly well and a few bomb that exam. A skewness near zero indicates a symmetric distribution like normal distribution. Now moving on to kurtosis. Kurtosis measures tail heaviness. Does your distribution have heavy tails with extreme values or light tails? High kurtosis means heavy tails. You get more extreme values than you would expect from a normal distribution. This matters because it affects your outlier detection. Low kurtosis means light tails, values cluster tightly, and fewer extreme values. The normal distribution has a kurtosis of 3. When analysts talk about excess kurtosis, they mean kurtosis minus 3. Here is a practical takeaway. Skewness and kurtosis tell you the shape of your data beyond just the center and spread. This shape affects which statistical tests are appropriate, how should you transform your data, and how you should handle your outliers. Always calculate these measures to reveal the important properties of your data. Let me bring all this together with a real-world example that I have modified slightly from the actual consulting world that I did. Imagine you are analyzing annual salaries for 100 software engineers at a tech company. Here is what a descriptive statistic tells us. Mean is $125,000. This means that the average salary, which is nothing but if you sum all the salaries and divide them by 100, because we have 100 employees, this is the number that you will get. The median is around $122,000. This is the middle value. Half the engineers earn less than this, and the other half earn more than this. Notice something important, that the mean is higher than median. This suggests that there are some high earners pulling the average or the mean on the upside. Standard deviation is $18,500. This is typical distance from the mean. Most salaries will fall somewhere in the range between 106,500 to 143,500. The range is between $95,000 to $185,000. The lowest paid engineer makes somewhere around $95,000, and the highest paid engineer is making $185,000. But remember, this tells us about extremes, not about the typical spread. Skewness that observed is around 0.45. This positive value indicates that the data is slightly right skewed. There is a tail of high paid engineers pulling the distribution on the right side. Now, here is my interpretation that I would present to the stakeholders about this data. Salaries are mostly concentrated around $120,000 with a standard deviation of $18,500. However, the data shows a slight right skew, indicating that we have some high earners as well. Specifically, there is a group of senior engineers and specialists earning significantly more than the median, which is pulling the mean salary up to $125,000. This actually means healthy, because for the company, it shows that you are paying competitive rates for the experienced talent. So this example shows how descriptive statistics tells a coherent story about your data. Let me crystallize the most important lessons from this presentation. First, always start with descriptive statistics. They tell the real story. Don't skip directly to models and predictions. You can't understand your data without these fundamentals. Second, don't rely on the mean alone. Always calculate the median alongside the mean. The gap between these two reveals something very important information about your data's shape. Third, variability matters as much as the central tendency. Understanding how spread out your data is essential. It affects everything downstream that you will perform. Fourth, visual inspection complements numerical summaries. You should always create histograms and box plots to see what the numbers are telling you. Charts always reveal patterns that the numbers might not will be able to uncover. Fifth, these fundamentals are foundations for hypothesis testing and inference. Everything we will cover in future presentations, be it confidence intervals, hypothesis stats, regressions, builds directly on this foundation. Descriptive statistics, as I said, aren't flashy. They will not win awards, but they are bedrock of competent data analysis. You should master them first. Thank you for working through this foundational topic with me. Descriptive statistics might seem basic, but they are where every data analyst proves their competence. In the next video, we'll build on this foundation and explore probability distributions, the bridge between the data description and statistical inference. If you found this video useful, valuable, please like, subscribe, and leave a comment in the questions. I will read every comment and I value your feedback. See you in the next one. Thank you.